All right, welcome today. We've got a very special guest with us, Ed MacDonald. This is Blake over at DZone Community Manager here. I'm so excited to have Ed with us today for another DZone Live. So thanks for watching across YouTube, Facebook, Twitter, and Twitch. Just a quick note of house cleaning. We've got a new containers trend report out. You can get that at dzone.com/research. But without further ado, I am going to turn it over to the person of the hour, Ed MacDonald, and he's going to drive it today, and we'll have a Q&A at the end.
Thanks for the introduction, Blake. As Blake said, my name is Ed MacDonald. I'm a senior software engineer and consultant for Solution Street. Check out our website, solutionstreet.com. Like Blake said, today I'm going to be giving an introduction to Kubernetes. Before I get started, though, I did want to mention, as I said, I work for Solution Street. We're hiring, so if there are any software engineers out there looking for a job, we're looking for full stack developers, data warehouse engineers, senior Java devs, Ruby on Rails developers, React, JavaScript. There's a link at the bottom there. I'm going to try to make these slides available. Certainly, let me go back. You can go to the YouTube video. You'll see my email. Email me for a copy of the slides. I'm going to provide them to DZone and try to get them linked to on the YouTube video. Blake just told me that's an easy thing to do. So yeah, we'll get you a link to the slides so you can click all these links. It's a PDF, so they'll all be clickable, easy access. So time to get started. So first of all, let's talk about what Kubernetes is. I don't know how many of you are familiar with containers, but that's kind of the core of the framework. And Kubernetes is just a framework for orchestrating containers. It's very well suited for applications that scale horizontally. We'll talk about that in a bit. But this is important. It can also accommodate portions of your infrastructure that do not scale horizontally, stateful portions of your infrastructure. Don't let people tell you otherwise. It's a common misconception. I mean, of course, Kubernetes was designed to scale horizontally, but it's a common misconception that you can't have stateful components in it. You absolutely can, so don't let that dissuade you from choosing Kubernetes to deploy your application. Okay, so how do you use it? The first part, one of the most important parts, is you have to package your application as containers. So that's a big step for people who aren't used to using containers. You have to build it into your pipeline. However you build your application, you now have to containerize it. And then you run these containers on what are called Kubernetes pods. We'll go into more detail about that later. And then you let Kubernetes manage the pods for you. So again, the big step is containerizing your application. Then you create some Kubernetes configuration and tell it how to manage these pods, which are running your containers. So why would you go through the hassle? And I'm not going to lie, it can be a hassle to set up Kubernetes. It's a lot of work. It's a lot of infrastructure. Cloud providers make it way easier, so you don't have to host your cluster in-house, but still you have to re-architect significant portions of your legacy applications if you want to move them to Kubernetes. If you're designing new applications, it's less of a hassle because you're starting from scratch, so you can design them with Kubernetes in mind. But yes, why would you go through the hassle? Well, first, Kubernetes can manage resources for you by changing the number of pods to meet traffic demands. So that's what we mean by horizontal scaling. As more customers come to your website, Kubernetes will automatically handle starting new pods to handle the traffic, and it will automatically load balance traffic to these pods. It can adjust compute resources to meet demands. This is a little bit of a white lie here in that it's technically not Kubernetes doing that. Typically, the cloud providers in which you deploy Kubernetes have implementation-specific ways of adjusting compute resources to meet compute demands. And we'll talk about this a little bit in more detail, but I'm more familiar with Azure. I've deployed Kubernetes to Azure. At my current job, I will be doing so to AWS, but I don't have a ton of experience with AWS yet. So I can speak to Azure. Azure's Kubernetes implementation is called AKS, and AKS will manage Kubernetes nodes for you. And we'll talk about nodes in a little bit. They're what your cluster runs on, but the node in the Kubernetes cluster is essentially what you're paying for in the cloud. It is the compute instance. It's the virtual machine. AKS will Kubernetes will manage the pods and distribute them across nodes. AKS will actually manage the nodes for you, so you can set up constraints where AKS will shut down entire nodes to save you money on compute resources if, for example, your compute resources aren't being fully utilized. And that's very important because that's one of your more expensive cloud resources. You've got bandwidth, compute, and storage. And of those three, I think compute is probably consistently the most expensive. And Kubernetes will replace unresponsive pods with new ones. So no more getting paged at 3 a.m. when a service goes down. Kubernetes will detect when a service goes down and just restart a new pod and throw the old one away. So I mentioned horizontal scaling. We need to talk about when can you benefit from horizontal scaling. So this helps you. This slide is intended to help you evaluate whether it's worth it or not to move your existing legacy applications to Kubernetes. And then the big question you have to answer is can your app benefit from horizontal scaling, or can you make some slight modifications so that it will benefit from horizontal scaling? The easy answer is if your app only consists of stateless components, then it can easily benefit from horizontal scaling. An example of this is just think of an app that converts Word documents to PDF documents. You upload a Word document, you get a PDF document back. You can spin up 10,000 nodes that do that. Any node can answer any request, and the life cycle of the request is just one request response. So there's no state that needs to be carried between requests. It doesn't matter which node is doing the conversion because it's just one simple process that runs, gets an answer. This is kind of the canonical example of a Kubernetes application, totally stateless. Another example, we're going to work our way down to from least complicated to most complicated. Your app has stateful components, but the stateful components are not the bottleneck. The example I always think of here is SETI at home. This was the search for extraterrestrial intelligence. They process radio waves from different portions of the sky, and they collect them, and processing the radio waves, I'm not sure what processing they do, but it's an expensive computation. So I don't know if any of you are old enough to remember this, but they had created a screensaver that you could install on your PC, and they would distribute computations to that screensaver. So while your screensaver was running, you were processing radio signals sent to you by SETI, and that was the bottleneck. Processing those radio signals was an expensive computation. I'm guessing, I don't know that this is true, but it certainly serves for my example here. I'm guessing that when the computation was finished, you sent a request back to them containing the result, and that was inserted into a relational database management system, which is something that by default, I'll backtrack on this in the next bullet, but by default doesn't technically horizontal. People don't scale databases horizontally, they scale them vertically. In other words, they buy more expensive hardware to handle more requests. So in this example, the database, although a stateful resource, is not the bottleneck. So SETI, had Kubernetes been around then, could have scaled it horizontally by creating compute nodes in Kubernetes and having them talk to a relational database management system. The third example, slightly more complicated, is if you've identified that your stateful component is the bottleneck, then the question becomes, can you find a way to scale it so that it's no longer the bottleneck? And then you can shift the bottleneck back to the compute and then put the compute in Kubernetes, for example. An example of this is if you've identified your relational database as the bottleneck and your app is a select-heavy application, so you've got a Postgres server and you're serving up a lot of read queries, but not a lot of inserts. In Postgres, for example, you could have the primary server replicate to a bunch of secondary servers, and you could have the secondary servers serve the selects. And you can, with Postgres, you can't do it infinitely, but you can scale a lot of secondary servers. And now you've moved the load. Again, if the load is read load. In other words, inserts still happen to the database, but if that's not the bottleneck, you've now distributed the load, and now the relational database is possibly no longer the bottleneck. Another example is if it's a write-heavy application, then you can shard your database, and this is the most complicated. This is a really big re-architecture for your app. I don't know, I'm not going to go into too much detail about sharding, but you essentially have a copy of your database that is sharded by, say, username. So all users from A through M end up in one instance of the database. They all get inserted there, and N through Z end up in another instance. Okay, time for some pictures. So I'm a visual learner. It helps me to see pictures of this. So this is just a very high-level deployment walkthrough of what deploying an application to Kubernetes looks like. First of all, you start with an application. Build your app in whatever language you want. I'm a Java developer, so for me, this app is probably a WAR file, or more typically now, a jar file. If you use Java Spring, it'll create jar files that you can just run as your application. So I build my app and package it as a jar file, for example. Then, like I mentioned earlier, in order for it to run in Kubernetes, it has to be in a container. The container solution I use, and the only one I'll talk about in these slides, is Docker. I know that there are other solutions. I can never remember the names of them. For me, Docker is the most prevalent, although someone is free to contradict me there. I know that there are other popular solutions. So yes, step 2, package your application as a container. Then you have to push that container to an image repository, a container image repository like JFrog or Nexus, somewhere that your Kubernetes cluster is configured to pull containers from. So that's one of the steps when you set up your cluster, is you have to tell it where its source of containers are from. And then you use a tool like Helm. I'll talk about that later. I hesitated to mention the name now until I talk about it later. But you have a way of pushing your pods, which are just YAML configuration files, to the Kubernetes cluster. And Kubernetes spins those pods up, and then it pulls your container into each of those pods. So this is a very high-level overview of what a Kubernetes cluster looks like, how it pulls, how you must deploy your application. And the key here is when you deploy a Kubernetes application, you're just pushing some configuration to a Kubernetes cluster that tells it how many pods do you want to run, where do these pods find their container repository, things like that. We'll get into more detail in a second. So like I said, really simple, right? So I was saying earlier how complicated Kubernetes was. So, okay, let's get into the weeds. First thing to talk about, let me back up a little bit. On this picture here, I just drew the Kubernetes cluster as a cloud that was all magic, right? The big thing that I left out of that picture, because it's kind of an implementation detail, are the Kubernetes nodes. As I mentioned earlier, these are the virtual machines that make up the Kubernetes cluster. So Kubernetes has to run on something. And I'm going to guess here that most people that use Kubernetes run it on virtual machines. You can actually run it on hardware, of course, but a lot of people, one of the benefits of Kubernetes is having someone else manage the hardware for you, like Amazon, AWS, or Oracle, or Google, or Microsoft with Azure. So a lot of people tend to run Kubernetes on virtual machines. And then all Kubernetes at a very high level is just responsible, the Kubernetes application, for scheduling pods to run on these nodes, making sure that they're up and running, moving them between nodes, etc. This again is I mentioned earlier, the little white lie that I told. It's not actually Kubernetes that can change the number of nodes to increase or decrease compute resources. It's the implementation of Kubernetes that can do that. So this is what Azure Kubernetes Service, AKS, does for you, or I think it might be EKS in AWS. I'm not sure about that, Elastic Kubernetes Service, but the cloud implementations of Kubernetes allow you to set up parameters that can change the number of nodes. So Kubernetes is responsible for scaling pods up and down. This is very important. The Kubernetes implementation, be it AKS or EKS, is responsible for changing the number of nodes in the cluster. And that last bullet there is how you save money by using Kubernetes, by letting the cloud decide how many compute resources you're using. Okay. As I go through this, I have a couple slides interspersed in here of different tools I've used. And I'll mention them briefly when I show the demo. And I'll mention again at the end of the demo, but I've checked these slides in and the actual code to run the demo. This is all checked into GitHub. There'll be a link to it on the last slide, so you're free to check that out. You can think of these tool slides as tools that you'll need to run the demo if you choose to do that. So Minikube is the easiest way to install a single node Kubernetes cluster on your machine. It's for development purposes only, but for any code you write, it looks exactly like a Kubernetes cluster because it is a Kubernetes cluster. It only runs on one node. It's made for development purposes only. You certainly wouldn't want to deploy your production app to Minikube. It would be kind of pointless because you're running Kubernetes inside of a virtual machine, deploying your app to it on your hardware, your local machine. So development purposes only, but I will use it for the sake of this demonstration. So here is a picture that I'm going to build up over the next few slides. Right now it's very boring. It shows our Kubernetes cluster, which consists of 2 nodes for example purposes. My demo will only have 1 node, and I'll show an update of that picture right before the demo. But right now we're starting out with a Kubernetes cluster that has 2 nodes, 2 virtual machines, probably each running Linux. So now the next Kubernetes object we're going to talk about are pods. Pods and not containers, and we'll get into the distinction in a second. A lot of beginners to Kubernetes confuse the two, but a pod is not a container. Pods are the fundamental building block of a Kubernetes application. A pod is a group of 1 or more containers that act or that work closely together to on a specific task. But pods do things that containers don't. So if you're familiar with Docker, in a Docker file, you just specify what gets installed to your container, for example, and then you build that container, and now you have a container. But then you need another tool like the Docker command line, or more commonly Docker Compose, to do things like set up volumes for your containers. And Kubernetes will do that for you. So Kubernetes, a pod, serves some of the purposes that a tool like Docker Compose does, and that it sets up volumes for your containers. One thing that pods do that Docker Compose doesn't do is pods also, well, they mandate that you specify health checks endpoints for the containers. So if we have time, I'll show some code. My containers have, in Kubernetes, the bare minimum is you have to show a liveness and a status endpoint. So, or I'm sorry, liveness and readiness, and they can both be the same endpoint. But this tells the Kubernetes engine how to query your pod and answer the question, is it up? Like Kubernetes will start a pod, and then it will query the readiness endpoint to determine when the pod is up. In other words, when it can start distributing traffic to it. And it will query the liveness endpoint periodically to make sure that it's still up. And if the liveness endpoint doesn't respond, Kubernetes will throw the pod away and start a new one, and then query the readiness endpoint until it's ready, and then it will put it into the cluster and start distributing traffic to it. So again, health check endpoints are what lets Kubernetes know when your pod is ready to start accepting traffic, or whether your pod is no longer able to accept traffic. And here's the Kubernetes eating its own dog food bullet. The Kubernetes software itself, like the software that we call Kubernetes, is just deployed as pods in the cluster. So this is a gross oversimplification. It's more complicated than this, but 2 pods that you can think of that Kubernetes deploys that are system pods to the cluster are the API and DNS. The DNS pod is used as a first step for name resolution for all the pods in the cluster. We'll talk about why that's important in a little bit. And the API is how you talk to Kubernetes. So Kubernetes exposes everything it does as a RESTful API. And the tools that we'll talk about, kubectl and Helm being the two big ones, are kubectl is a very thin wrapper around the Kubernetes RESTful API. In fact, kubectl has config options that will show you, if you set like the maximum verbosity, it will show you the HTTP request it's making to the cluster. It's a great way, for example, if you want to write a custom application, it's a great way to explore the API. You can just be like, well, this is what I would do in kubectl, and just turn up the verbosity. You can see the requests it make, and then you can just yank those into your application and make the same request. Okay, so let me talk about the sample applications for my demo. Let me see how we're doing on time here. Okay. I wrote two applications that do nothing other than suggest a random subreddit. I wanted to keep them simple to just show a couple of the features of Kubernetes. One of them is stateless. So we've talked about, the two big types of apps you're going to deploy to a Kubernetes cluster are stateless or stateful. One of my apps is stateless, and it just selects at random from a list of 280 subreddits. The list never changes. It's stored in memory. It doesn't need to store anything anywhere. By that, I mean it doesn't need to persist it to disk. The list lives in memory. And then the other app is stateful. It also selects from a random list of subreddits. However, once it selects one, it removes it from the list, and then it persists the list to disk so that the next time it services a request, it pulls the new list. And essentially the difference between the two is, and we'll see this on the stateless app, if you keep refreshing, you're always pulling from the same list. On the stateful app, and you're always getting a random one. So there's no way for the stateless app to guarantee that you will see every subreddit before the list cycles. The stateful app provides that guarantee. So the first time you'll select from a list of 280 subreddits, the next time 279, all the way down till you see them all, and then it will refresh itself. Yeah, and then it uses the updated list to service the next request. Okay, now to talk a little bit about pods, and this is going to get to the crux of the difference between stateful and stateless app. Pods can come and go. They're replaced if unresponsive, like I mentioned. If the liveness check doesn't respond, Kubernetes kills the pod and starts a new one. It can be deleted on one node and added to another, moved. So when Azure Kubernetes Service, AKS, when it scales down the nodes in your cluster, it has to do something with the pods that were on the node that it's turning off. And what it does is it moves them to the other node, but there's no such thing as moving a process from one computer to another. So the way that Kubernetes accomplishes this is the node that it wants to shut down, it kills all the pods, stops distributing traffic to them, then kills them all, and then just starts them up on the other node. This is the most important thing to remember, is you can't prevent either of these things from happening. So when you're designing your application, don't assume that you can prevent a pod from being restarted. Technically, there are ways to control this somewhat, but don't get into the habit of doing it. I'm not going to talk about them, mostly because I can't recall them from memory, and I haven't mentioned them anywhere else in the slide. But it's better to just assume you can't prevent these things from happening. So what happens when one of these pods dies or is moved? Well, by default, volumes don't follow pods. So volumes are the things that the pod maps for you so that your containers can see and store things in the volumes. By default, host names don't follow pods. So every pod has a host name. For stateless pods, it doesn't do you any good to know the host name, because if the pod moves, it won't be addressable by the same host name. So like I said, this is not a big deal for stateless applications, because stateless applications, you don't care which pod you're talking to. You are okay with the Kubernetes load balancer taking your traffic and farming it out to whichever pod in the application it sees fit to do so. Your application, your client application, doesn't care about the specific pod it was talking to. It definitely needs to be addressed for our stateful application. It might not be obvious yet for the host names, but certainly the volumes, because remember, our stateful application is writing a file to disk, and if one of the pods in our stateful application gets moved to another node, by default, and we're gonna show how to resolve this, but by default, it would not, that volume would not follow it. Now, I've been talking about Docker a lot. So for people who aren't familiar with Docker, it's probably, if you're new to Kubernetes and you're new to Docker, certainly learn Docker first. Docker, like I said, is my favorite container manager. I know that there are alternatives. I forget the names of them. And I think I would say that Docker is the most popular, but I'm not sure if that's true anymore. I know that some of the other ones are gaining ground. But why do I use Docker? For the purposes of this demo, we need to package our applications in a container. I chose Docker containers. And the Docker command line tool will allow me to publish the containers I create to Minikube's Docker server. So when you install Minikube, I run on a Mac. I think it's the same on Windows. It's slightly different on Linux because I don't think it needs to install a VM. But on Mac, it installs a VM, and then that VM, it configures it to be a Kubernetes node and installs the Kubernetes software, but it also installs a Docker image repository that you can push your images to, because that Kubernetes cluster, Minikube, needs to pull those images from somewhere. So that's, Minikube is more than just a Kubernetes cluster. It's also a Docker image repository, is the short there, the short description there. So let me, yeah. So now this picture shows what our two applications deployed to a Kubernetes cluster look like. We have the Stateless app, which is deployed as 3 pods, and the Stateful app, which is deployed as 3 pods. You'll notice here that I've put hashes to indicate that these are randomly generated strings. So our Stateless app pods will be named Stateless app hyphen something, but the something is a randomly generated string. Not so for the Stateful app. They will have predictable names, and Kubernetes just indexes them from the number of pods that you decide that you want in your stateful set. And we'll talk about what a stateful set is in a second. But it just indexes them. So stateful app 0, stateful app 1, stateful app 2. And any service you have that knows how to use the Kubernetes DNS resolution to resolve these names can reliably resolve IP addresses for these pods, if that makes sense. That's oversimplifying, but that's a good way to think of it. So I've talked a lot about pods. Technically, if you want to, you can use a tool like kubectl to deploy a pod right to a Kubernetes cluster, and then you've got an application. Nobody does that though. Instead, they use controllers so that they don't have to create pods directly. Controllers allow you to specify additional metadata, like how many pods you want and when you should scale up and when you should scale down. So if you're deploying your app manually as pods, then you're responsible for creating more pods or creating fewer pods, which is why nobody does it. Instead, they use controllers and say, I want anywhere between this number of pods and this number of pods, for example. And here are the constraints when you should scale up or scale down, etc. Yes, so instead, you just let a controller manage the pods for you. So the first controller we'll talk about are ReplicaSets. ReplicaSets allow you to, allow you to state how many pods you want, like I already mentioned. This is the important bullet here. Pods are treated as if they were stateless, so a ReplicaSet is a way for managing pods in a stateless application. From the application's point of view, all pods in a ReplicaSet are indistinguishable, and that's essentially just restating bullet number 2. That's what I mean by stateless. Now you'll see deployments mentioned a lot because they are what people use instead of replica sets. It's just a replica set with more features. I'm not going to use those features for this demo, but I just use deployments, and I mention it here because this is what Helm produces by default when you create a skeleton Helm project. So, and when we look at the Kubernetes dashboard, we'll see that under the covers, the deployment creates a replica set for us. But yes, you'll see deployments used in production. Like I said, I don't want to talk about the extra features that they provide, so it's easier to just think in terms of replica sets. So what do we do for our stateful applications? Well, stateful sets manage pods that are required to have state. Namely, pods in a stateful set each have a persistent network identity, and they each have persistent storage. And persistent here means that they follow the pods. So when the pod moves, when a pod is stopped and restarted, the new pod that gets restarted to replace an existing pod that had been stopped will have the same name as the pod that it replaced, and it will have the same persistent storage. So when the Kubernetes brings that pod up and maps its volumes, it will map to the same persistent storage. This is very important for our stateful application. I mean, this is literally what enables it to work. Now, another tool I've been talking about periodically is kubectl. So kubectl is a command line utility that, like I mentioned, is a very thin wrapper around the Kubernetes RESTful API. So it allows you to manage your cluster. You can use it to update components in your cluster. You can use it to inspect components in your cluster. And you can even use it to create components in your cluster. But we're going to use another tool for that. Really, I only use kubectl in production to inspect components in the cluster, because updating components in the cluster, if you use kubectl to update a component in a cluster, for example, if you were to update a pod, there's a very good chance that there's a deployment that's already managing that pod, so your update might not even be permanent. So you can use it to update and create components in development, but even in development, I don't use it to create components. Use another tool for that, which is another tool I've mentioned, which is Helm. And Helm is just a tool for packaging and deploying your Kubernetes application. At its simplest, Helm is just a collection of YAML files. So all the things we've mentioned, deployments, stateful sets, replica sets, we're going to mention services, all of these things have what's called a manifest, which is a way to define it, and it's all defined in YAML. So the Kubernetes API is, at its simplest, a way for sending post and put requests that contain YAML and issuing get requests to view YAML. So if you want to deploy something to Kubernetes, you send it a YAML file declaring the state that you want the cluster to have, and then Kubernetes works to converge to that state. That's like the 10,000 foot view of Kubernetes. And Helm is just a way of packaging all those YAML files up, all of the manifests that declare your application. And I mean, it literally just creates a zip file and then provides some wrappers around API calls to push that zip file to Kubernetes and deploy the application. So now we add two more blocks to our diagram. We have our stateless app deployment and our stateful app stateful set. We'll talk about this a little bit more in a second, but you can think of these as just managing pods. There are different ways to manage pods. So the stateless app deployment, for example, controls the lifecycle. It's responsible for all of the pods in the stateless app. It's responsible for monitoring them. It's responsible for restarting them when they stop responding, and it's responsible for moving them between nodes in the cluster. Take a break here to see if we had any questions. Do not yet. Okay, so let's talk about persistent storage. Stateful set does more than the replica set or deployment and this is kind of the extra services it provide over that makes it suitable for managing a stateful application. Stateful set pods can have persistent volume claims, and we'll just show a picture of what those are in a second. They're used to request persistent volumes. And persistent volumes are volumes that survive pods being moved or replaced. So this becomes clearer when we see it in the picture. So Here we see each of our stateful apps have a persistent volume claim, which is just part of the configuration of the pod manifest that we put in the deployment manifest. And you can think of these persistent volume claims as just a set of implementation-specific coordinates into whatever external storage media you're using. So in Azure, this could be blob storage. In AWS, this could be S3 buckets. So this persistent volume claim has all the information you need to essentially reference a volume, a bucket, some chunk of space on a disk somewhere on some external service, so that when Kubernetes moves, for example, stateful app to pod from node 2 to node 1, it carries its claim with it. So when it comes back up on node 1, it will have a set of coordinates that will allow it to map the same volume that it had mapped while it was on node 2. And that is all of the magic. That is how Kubernetes guarantees that your stateful app pods always have access to the same files on disk. Now we're going to talk about a headless service. So I created these slides maybe almost a year ago now. So I don't know if this is still the case, but it was when I created them. And I think maybe the Kubernetes team was working on a different solution to this. But it used to be, and I don't know if it still is, certainly my application still works with the latest version of Kubernetes because they're pretty good about being backwards compatible. But stateful sets are the way that Kubernetes stateful pods maintain their host name. So it's used by the Kubernetes DNS pod that we showed in the diagram earlier. And like I said, it just allows pods to keep their host name by keeping track of their IP addresses, even when it changes. I don't want to go into a lot more detail than that. The way I think of a headless service is it's basically just a bind configuration file that maps host names to IP addresses. And so the headless service is responsible for when stateful app 2 moves from node 2 to node 1 and gets a new IP address. It's the headless service that's responsible for updating this record right here to say this is your new IP address, so that you can always refer to this by host name. Because moving from node 2 to node 1 certainly does not guarantee that you get the same IP address. The headless service is responsible for managing that. And finally, now we're finally getting to the end of this picture so that we can do a demo. Last thing I think we have to talk about is load balancers. So load balancers have an internal and a cluster IP address. We'll talk about what those are in a second. They can also have an external IP address. They distribute requests sent to either of these IP addresses to all pods targeted by their selectors. So load balancers are one way that you can expose your app to the outside world by giving it an external IP address. This is how I set it up in Azure. Usually there's a cloud-specific, implementation-specific way of assigning the external IP address. There's also something called ingress services that I haven't used, because Azure Kubernetes Service essentially gives you an easy way to assign an external IP address to a load balancer. But they also have an internal cluster address, which is essentially the address to one of the nodes in the cluster, and it will distribute any traffic sent to any of those IP addresses. It will do the load balancing between pods in the application for you. So here's what those look like in the picture. So the key takeaway here is that load balancers are one service that's responsible for managing pods, and the stateless app, the deployment and stateful sets are another way of looking at a group of pods. So when we talk about deployments and stateful sets, they're responsible for managing the life cycle of each of a collection of pods, whereas load balancers are responsible for distributing traffic to those pods. So there are multiple things in Kubernetes that operate on the same set of pods, if that makes sense. So now it's time for a demo. Briefly, I want to talk about what I'm going to do in the demo, because I've already taken some of these steps in the interest of time. I use Minikube to start a Kubernetes environment. I've already configured Docker to talk to Minikube's Docker host. I've already built our 2 sample applications, packaged them as Docker containers, and pushed the images. All of the scripts I've used to do all of this are all in the Git repo, so you can study them to your heart's content. I've already run Helm to deploy our Kubernetes components, and I've already proxied local ports to our load balancing services. So essentially the app is up and running in Minikube on my machine. And now for a little bit of truth, again, this is a very simplified architecture. Our stateful app only has 1 pod. The stateless app has 3 pods. So this is the architecture of the app that I'm going to demo. I'm going to essentially open my web browser and talk to these load balancers, and it's going to distribute traffic across the stateless app pods, of which there are 3. In the stateful app, although we'll show an example of how to scale this and we'll get more pods, but to begin with, it's only going to be sending all traffic to the only pod that's in that application. So without further ado, let me briefly show you. This is the Kubernetes dashboard. So this shows you all the objects I've been talking about. I have a deployment, I have a series of pods, I have a replica set, which is interesting because, like I said, I'm using a deployment, but under the covers, the deployment manages a replica set for us, and I also have some stateful sets. So down here, we can look at all our pods. We see the stateful app only has 1 pod. We see that there are 3 pods in the stateless application. Yes, okay, good. I'm presenting. I'm showing my browser window now. So this is the stateless application. So one thing I want you to watch is, remember, I'm telling you that this is being distributed among 3 pods, but there's no reason for you to believe me. So when I wrote this application, like I said, it pulls from a list. It gives you a link to a random subreddit. I can make this bigger. But it also shows the host name. So watch when I refresh this, how the host name changes. Do it a little bit slower so you can see it change. Doesn't change every time. But for me, that's my proof to you that the, again, I'm not hitting different IP addresses here. I'm just hitting localhost, and this port is being forwarded to the load balancing service in the cluster. That's proof that we're distributing requests across the 3 stateless apps. Now in the stateful app, it's almost the same, except, excuse me. I've also showed the remaining subreddits. So remember when I said that each time we request a subreddit, it pops that one from the list so that it never shows it again until we get all the way to the bottom, and then it recycles the list. So here we see, and this is going to be important for something I'm going to demo in a little bit, every time I request a random subreddit, it's removed from the list, and the number of remaining items to go through shrinks by 1. So we'll bring this down to 240, and it started at 280. Those are the apps. We're going to demo some things that make it a little more interesting, but yeah, pretty simple. So the first thing I want to do is, now if you go to GitHub and check out the repo, like I said, these are all the scripts that I've automated all this. So I've run 0.0 through 0.5. So I've started Minikube, configured Docker, et cetera, all the way up to bring up the Kube dashboard. So the first thing I'm going to demo is I'm going to kill this stateful pod to show you, number one, that Kubernetes will restart it, but more importantly, when Kubernetes restarts it, it will maintain its state. If this were a stateless pod and I was showing you the number remaining, you would expect it to go back up 280 because that file is stored on disk. However, you'll see that when I kill this pod, Kubernetes will restart it. Did I just see a question? Someone just asked what's the URL to my GitHub. We'll post that in the slides. It will be on the last slide, so keep an eye out for that. Yeah, and like I said, I'm going to do my best. Well, I will make sure that these slides get posted to the YouTube channel. And if that doesn't happen, certainly email me. My email, again, was on the first slide, and I can post that in the chat too. So Okay, so I'm going to bring up I need to shrink this back down. I want this window up because when I kill this pod, what we're going to see is that our stateful set will go into an unhealthy state and our pods will go into an unhealthy state while Kubernetes recognizes that the pod has been deleted, and then it will bring it back up and it will, again, converge to a healthy state. So that's probably worth showing what this does. I'm using kube control, is all I'm doing is I'm deleting the pod by name. So this is one of the uses of kube control, again, for when you're playing around on your development machine. Or you can do this. This is actually safe to do in production if your application is designed correctly, because like I mentioned in the slides, never count on pods surviving. You have to count on them being deleted out from under you, like when they're moved between nodes. So it's always safe, hopefully, to do this. So let me kill the stateful pod and make sure that I get back here in time. Okay, so now we're going to watch. Hopefully, yep, there we go. So we're missing a quarter of our pods because we have 4 pods, 3 stateless, 1 stateful. And the entire stateful set, we only have 1 of them, is in a bad state. And now, wait for it. Oh, Kubernetes is thrashing a little bit. This is fine. It will figure it out. We can watch this from the command line too. And I think it's going to be back in it. So this kube control get pods just shows you all the pods in the cluster. And I see that Stateful app has this one. For each pod, it's showing you the number of containers in the pod and the number that are, how many of them are ready. So this number here, this 1 of 1, is not referring to pods. This is 1 of 1 container in the pod. But you can see that for the stateless app, for example, we have 3 pods, where the stateful app, we only have 1. Like I mentioned earlier, it is not uncommon at all for a pod to have multiple containers. It just happens that this is a very simple example, so all of our pods only have 1 container. And now when we come back here, we see that Kubernetes has converged to a healthy state. And now, the really important thing to look at is the number 240. When I refresh this, we would expect it to go to 239. And there it did. Yeah, I missed that. I wasn't watching. Yes, it went to 239 and we got a new subreddit. So now what I want to do is I'm going to prove to you, well, to kind of show the counterexample, instead of, I'm going to create a new instance of our stateful app. So I'm going to take the same container that I deployed when I stateful app it. Remember, that's a Docker container. And in the correct example I showed you is I deployed that stateful version of our app into a pod that's managed by a stateful set. What I'm going to do now is deploy yet another pod. I'm going to create a new deployment, which is going to manage, I think actually technically I'm creating a replica set, but I'm going to create a replica set to manage the pod. And again, replica set is what you use for stateless apps, but I'm going to deploy my stateful app in it to show you the interesting ways in how it breaks. So the first thing I'll do is, well, we can take, no, I'll show that later. So I'm going to run stateless stateful app sh, which is going to deploy the stateful version of our app in a container that is managed by a replica set, not a stateful set. We'll see over here. We'll see Kubernetes go unhealthy. Will it recognize there's a new pod in the cluster and it's waiting for that pod to come up? And I call this confused deployment to indicate that it's not correct. So we still have our stateful app. pod, and we still have our 3 stateless app pods. We're just deploying a new app. Now, when I refresh this, okay, so this looks just like our, let's just see how we're doing on time. All right, this looks just like our stateful app did, right? Like we're still counting the remaining subreddits. Refresh, refresh, refresh. It counts down, all is expected. Now the question what happens is, what happens if we kill this pod? So now I'm doing what I'm calling killing the confused pod. Let me get back here. Bring this up. So again, just to be clear, I'm deploying the pod, the stateful app pod managed by a replica set. I'm going to kill that pod and allow the replica set to bring it back up. But what the replica set is not going to do is preserve the name, which we don't care about for this example, but more importantly, it's not going to preserve the volume that the previous pod was mapped to. So here we see one of our replica sets is in an error state. We're waiting for the pod to come up. Kubernetes is thrashing a little bit, but it will figure it out. When I say Kubernetes is thrashing, I don't know if we're going to be able to see it here. Oh, we are seeing it. So when I say Kubernetes is thrashing, Kubernetes will restart pods while it's, I mean, I'm running a Kubernetes cluster on my laptop, which has limited resources, and sometimes they don't come up in the amount of time that Kubernetes expects, so it shuts it down and restarts it. That's all I mean by thrashing, is it's restarting pods. I could make it thrash less by increasing the amount of time it's willing to wait for a pod to come up, which I probably should have done, but then I wouldn't have been able to talk about this, so it worked out well. But now it has reached a consistent state, so all the pods have come up in the time that it expects them to come up in. But now we're going to notice this is our stateful app, but it got moved or it got stopped and restarted, and I'm telling you that it didn't get the same volume mapped. So now when we reload it, it's going to load a file from disk. It's going to find that that file is not there anymore because it's not the same volume, so it's going to reinitialize itself with the same 280 subreddits. So there, the number went back up to 280 instead of going from 264, I think it was, to 263. Let me get this back down to size. So let me see. All right, I think I need to be done at noon, so I'm going to zip a little bit. So I had a slide here. I want to get through the back material and give time for questions. So I've only got 2 more slides here. And if there are no questions, we could go into a little bit of code. So I just want to mention this is a summary of the resources I used. Here's the answer to the question where the GitHub repo is. It's my username is E MacDonald, Kate's Kubernetes. So I didn't mention this. K8S, for those who are unfamiliar, for whom this is their first introduction to Kubernetes, you will commonly see it abbreviated that way. So K8S is the same as Kubernetes. I used a bunch of tools to put this together, LaTeX and Beamer, 2 of my favorite tools. Highly advise you check them out, but they are kind of esoteric. I used Kotlin to build the applications because it enabled me to write even less code. I use Spring Boot, which is extremely popular with the microservices community. A lot of microservices are written using Spring Boot and deployed to Kubernetes. I used Gradle to build the apps. I used a tool called Dia to build all the diagrams that you've seen in the apps. And I got the bulk Reddit data from this website here. It's just a website that has bulk Red data. I did a bunch of processing on it because I didn't want to be embarrassed in a demo, because choosing a random subreddit is a very risky undertaking. So I filtered the list down to 280 that looked pretty safe. I didn't read all of them, but I filtered on some topics that seemed like they would be pretty safe and excluded any that were known to contain not safe for work content. So yeah, just a warning. If you go here and download subreddit data, you're getting all of the subreddit data, so be prepared for that. A note on capitalization. I agonized over what to capitalize. I capitalized all the important Kubernetes nouns. Some didn't quite make the cut, like cluster and component, and I cannot bring myself to capitalize anything that I type at the command prompt. And with that, I think Blake is going to come back on and take care of the Q&A, but now I'm ready for questions. Yes, I see more questions about posting a link to the slides. Yeah, we're going to do that. We're going to post the slides on the YouTube channel. However, while I have the questions up, sorry about this, I will just put, rather than having the question slides up, I'll just put this slide up, which has my email address. So certainly contact me and I can email you a copy of the slides. We'll also post them on the YouTube link. So.
Yeah, so thanks Ed, for that. And then across wherever you're watching us from, whether it's YouTube, Facebook, Twitter, or Twitch, you can put in your questions for us and we'll do our best to answer them. We'll also be putting up links to the where you can get the slides and also to the repo, so you can have that as well. So if you have a question, go over and put that into the comments or to the chat, and we'll do our best to address those.
So I'm reading the chat here, so ask away. If you asked a question earlier that I missed, certainly ask it again.
Yeah, so we've got one from in here on Knative and Kubernetes. What's the difference?
I don't know the question, or I'm sorry, I don't know the answer to that. I don't know what Knative is. So yeah, I apologize for that. Someone's asking when there will be a Docker session. That's a good question. I don't know. Check the DZone website for that. Maybe Blake knows the answer. I don't know if there's anything planned for Docker. I imagine that probably there are talks on Docker.
Yeah, that's great for Docker. We didn't have it for today, but we'll definitely look into doing one for you. Thanks.
Yes, another question about the slides. We're going to post those on YouTube. I'm going to email the slides to Blake, and we'll get them posted on the YouTube channel. Can we use Kanaba for Kubernetes? I don't know what Kanaba is. If you could clarify, but I don't think I'm going to be able to answer that question. Monitoring, that's a good question. When I've used Kubernetes, I've typically used a separate monitoring tool like, I can't remember it off the top of my head. Certainly nodes in your Kubernetes cluster can communicate with it, whatever monitoring tool you have. I think the different clouds have different monitoring tools you can use. From a Kubernetes point of view, Kubernetes monitors your nodes via the endpoints you provide. Actually, I have some code up on the screen here. So when I mentioned that everything in Kubernetes is just a YAML file, here, when I talked about our deployment, here is the deployment that deploys our the stateless app that I demoed. And in here, you see liveness probe and readiness probe. This is how Kubernetes monitors, like a visualization tool. Let me see here. Well, let me finish talking about this. This is how Kubernetes monitors your pod to determine if it's ready to have traffic sent to it the first time it starts, and whether it continues to be ready. In our case, they're both the same. These can be different, which is why, in other words, you can have a readiness probe that is more expensive, say, than a liveness probe, more expensive in terms of how long it takes. These can't be very expensive to compute because Kubernetes pulls these by default, I believe, every 5 seconds. So, and yes, I'm sorry, Kibana and Grafana, yes. You can certainly integrate Kubernetes with Kibana. I can't remember the name of the tool. You can, just like you would install monitoring tools on your applications, you can certainly install processes that emit any metrics you want from your Kubernetes nodes, and you could publish them to Kibana and then use a tool like Grafana to visualize it. There's nothing preventing you from doing that. Again, because you're the one responsible for creating the Docker container. So a simple Docker container may just have Java and your jar file to bring it up. But you can certainly also install monitoring tools on the Docker containers to publish any metrics that you want to collect. Graphite, that's the one I was thinking of. Graphite collects graphics, collects metrics. Grafana displays them. So yeah, you can publish. I think the way Graphite works is that you install a utility in your container to publish metrics, and then yes, you can. But you can configure Grafana to point to Graphite to view those metrics, like time series graphics, stuff like that. I'm looking to make sure I didn't miss anything. I see the control plane. Is that the default on Minikube? I think the control plane is what I'm referring to as the API. Minikube does have a control plane, I believe. I didn't go into that into the slides though. When I lump together the Kubernetes software, that's kind of one of the components I'm talking about. Can we use Kubernetes with VMware Cloud for AWS? If you're going to use Kubernetes, I mean, you can. So you can. Well, I'm not exactly sure what VMware Cloud is, but I'm gonna talk. There are two routes you can go in AWS. You can create your own EC2 instances. So you can use a tool like Terraform to provision a bunch of EC2 instances. Then you can take on the responsibility of installing the Kubernetes components onto those nodes so that they become a Kubernetes cluster. And then you can write custom provisioning software to manage those nodes for you. That's one way to do it. And that is almost analogous to buying your own machines and installing Kubernetes directly on them. In other words, you've taken full responsibility for managing the Kubernetes, the EC2 instances, which you've now provisioned as nodes in a Kubernetes cluster. Or you could go the easier route, and I might be getting the name wrong, so I apologize for this. In Azure, I know for certain that it's called AKS, but I think in Kubernetes it's called EKS. But basically, Azure, Google, AWS, Oracle, they all provide a cloud-specific Kubernetes cluster that is a little bit more abstract than managing your own nodes. So with AKS, for example, you can say things like, I want my cluster to have between 3 and 10 Kubernetes nodes, and you can specify the instance types that you want them to be, so they can be high compute or low compute. And then it will manage provisioning those for you. It will manage installing the Kubernetes software on them. It's a much easier route to go. If you're already using AWS, I would recommend you use EKS instead of provisioning your own EC2 instances. But you might have a use case. You do lose a little bit of ability, and I'm not exactly sure what those abilities are, but I'm sure that there are use cases where you would want to use EC2 instead, but it's a lot more work. So that use case, there has to be value in it. So. So remember when I said I use Docker, and I can't remember what the other solutions are. So someone just asked the question if there are any advantages of Containerd over Docker and whether Docker is going to be deprecated in Kubernetes. So I'm guessing that Containerd is one of the other containers, a competitor of Docker. I personally don't think Docker is going to go away. I think Docker continues to get more popular, but there are alternatives. So I'm not aware of any efforts to deprecate Docker in Kubernetes, but I can't say for certain whether or not that's going to happen. That's a good question, though. All good questions. So yes. Looking through, I don't see any more questions. So going once, going
All
twice.
right, so
Oh,
let's.
we got one. Yeah, that's what I was saying. There are use cases. So the question is, what's the advantage of building your own master node, the DIY cluster versus EKS, AKS? There are advantages, and I'm sorry, I don't know what they are off the top of my head. There are. I knew the answer to this at one time, but maybe it gives you more control over ingress or something like that, or maybe you have fewer restrictions on what public DNS resolves to it. I can't remember off the top of my head. Yeah, I'm sorry. I would need to know more about the actual Kubernetes software itself, and I'm much more familiar with just the API of deploying applications to Kubernetes. I'm perfectly content to just let EKS or AKS manage it for me.
Well, that's great. So we're just wrapping it up here. If you got any other questions or like the event today, let us know. In the chat, I put a link to a post-event survey. So take the survey, let us know how we're doing. We definitely hope you enjoyed the time with that today. Our next live DZone event will be tomorrow. We're doing a very special CI/CD panel, so don't miss that. There's a link in the chat for that as well. Thanks today to our very special guest, Ed MacDonald. We will be putting a link to the repo and to his slides. We also put a link to Solution Street, where Ed works, in the chat. So we've got lots more DZone Live events coming up. So in the post-event survey, you can let us know if you want to see something on Docker or what other types of stuff you want to see. So this is Blake over at DZone, and I'll let Ed sort of wrap it up today. We had a really great, exciting Q&A and a really great presentation. So huge thanks to you, Ed, today. So take us out.
Yeah, thank you, everyone. I really enjoyed this. This is the third time I gave this talk. So yes, thank you for the questions. It's much more fun when people ask questions, so I certainly enjoy it. And yeah, I hope to do this again sometime. So thank you very much.